All right, I'd like to tell you about some work that's been ongoing here, initially with an undergraduate, Shauna Story, who graduated a few years ago, and with Justin Bergfield, a former PhD student, and actually also with my dad, who's a co-author of the paper. He's an organic chemist and helped us understand some of the organic chemistry. And just accepted for publication in ACS Nano as of Monday. So we're interested, I've shown you this picture before, we're interested in these kind of systems. For instance, this could be any kind of nanostructure. Here we have some electrodes, a source and drain that could flow some electric or heat current from here to here. And then what we're interested in this talk is a scanning probe of this system, in particular to probe the temperature distribution within the nanostructure. So here's an example of one of the calculations I'm going to show you later on. This is a graphene nanoribbon. It's attached to metal electrodes at either edge here, a cold electrode and a hot electrode, and in the color scale is shown the local temperature as measured by a scanning probe thermometer with sub nanometer resolution. Of course, this is still only a theoretical thermometer because the current state of the art is not quite there, but that's an indication of what you should see if you could do a measurement with that degree of precision. And notice that you don't just have a temperature gradient from hot to cold, but you get these quantum oscillations. I'm going to argue later that these quantum oscillations can be interpreted as being quite analogous to the actions of a Maxwell demon, and we'll have to see how the laws of thermodynamics, or what feature of the quantum system actually makes it so that the actions of such a demon don't violate the second law. So let me start out. I usually just assume that everybody knows exactly what Maxwell's demon is, but that since this is a colloquium, it's better not to make that assumption. Well, anyway, this is the same Maxwell as in the Maxwell's equations. He was one of the founders of the field of statistical mechanics, and in particular, along with Boltzmann and Gibbs, helped to understand what the second law means microscopically. And so in the process of doing that, he came up with this Gedanken experiment to illustrate the statistical nature of the second law. So here's a nice drawing by George Gamow. Imagine that you had, for instance, a container partitioned into two equal volumes, and it's full of, let's say, equal numbers of oxygen and nitrogen molecules. So that would be like the maximum entropy situation. But then you have this little microscopic demon in here, and if he sees a nitrogen molecule approaching from the left, he opens the door and lets it through. But if he sees an oxygen molecule coming, he doesn't let it through. And similarly, as you can see through the wall, he lets the oxygen molecules come through from the right to the left. And after some time, he can completely undo the entropy of mixing of the two gases, and so we would have just, let's say, oxygen on the left and nitrogen on the right. And this would be a manifest violation of the second law of thermodynamics. The particular version of the demon, like I said, this Maxwell demon Gedanken experiment, it can be, you can imagine many different realizations of it. That's one that I just told you about. The most common one, and the one which I'm going to be interested in here, is the so-called temperature demon, where the demon opens and closes a door. Let's say heat allows fast-moving molecules to move from A to B when they approach his little door that he controls, and he allows slow-moving molecules to move from B to A, and after some time he then has taken the system that was in thermal equilibrium and he separated it out into the hot and cold parts. This has led to a transfer of heat from a colder system to a hotter system, which again is a violation of the second law of thermodynamics. And of course, if you can do that, any one violation of the second law is as good as any other, then you could also make a perfect heat engine that converts thermal energy directly into work without respecting the Carnot limit, and Maxwell demon could do that too. So are there any questions about Maxwell's demon before I move on to more mundane topics? There's a lot of thought that's gone into this over the years. Anyway, hopefully that gives you an idea what it is. So now let me talk about a particular type of heat engine, and that's a thermoelectric. A thermoelectric is just a heat engine where the electrons are the working fluid. So the figure of merit for such a electronic heat engine is ZT, and it's equal to the product of the thermal power squared times the electrical conductance times the absolute temperature divided by the thermal conductance. And what does this figure of merit mean? Well, when ZT goes to infinity, such a thermoelectric heat engine approaches Carnot efficiency, or it achieves Carnot efficiency when ZT is infinity. So here are some materials, some of the best thermoelectric materials, and you see that ZT is not approaching infinity. It's actually more like approaching 1 in the kind of best materials that there are. And unfortunately, ZT approach of order 1 is not really competitive as a heat engine with more traditional heat engines based on compressing gases. So that has meant that thermoelectrics are basically a niche field. They have not replaced more traditional heat engines. But they have their applications, such as in space probes and things where you don't want to carry around a compressor and so on. But if one could just make them more efficient and or cheaper, then there is waste heat everywhere around us, right? Because every process, almost every process produces waste heat. I'm talking here, producing hot air. If we had some thermoelectric, clothing on me, we could harvest some of that waste heat and make useful electrical power out of that. But in addition, actually one of the things that's closest to market is a number of automobile companies in the last 5 years have introduced thermoelectric coatings of the exhaust headers of automobiles and catalytic converters. And they're able to harvest enough electrical power that they can do away with the alternator, so they just use the thermoelectric power to recharge the batteries, and then you can start the engine and whatnot. So you can increase the efficiency by something like 5% of the car in this way, but if you just had more efficient thermoelectrics, you could do much better, and if they were cheaper, you could also increase the range of applications. So what can we do to make them better? Well, this is not... Okay, so the state of the art of current technology is something like ZT around 1 and thermal power of a couple hundred microvolts per Kelvin. So one way that one can control things at the quantum scale, similar to what the Demon does in the gas that I talked about, is using quantum wave interference. So here's an older project that I've talked about a few times before, but essentially one arranges a nanostructure so that the quantum waves trying to get from here to here have destructive interference, and then by perturbing the waves you can let some through, and that's a way of controlling the motion of the electrons at the quantum level. And this is a basis of a US patent. Hopefully we're going to get very rich from this, although I'm not holding my breath. But this does suggest that there are ways of controlling quantum mechanical particles at this scale, similar to what the Demon is supposed to be able to do in the gas. And in a system very similar to this, indeed, we see that we can get a very large, very efficient thermoelectric engine. So here is basically, it's called polyphenol ether molecule, where this central block is repeated n times. And you see for n equals 6, we get a ZT up to about 7 and a thermal power of about 1,000 microvolts per Kelvin. So this would be a lot better than current technology. Now the question is there some connection between the way that the wave mechanics is controlling the motion of the electrons here and the fact that you're getting such large values of ZT? Well, in order to understand or even to pose, can I finish this thought? To be able to meaningfully pose a question like that, you have to be able to look at what is happening microscopically within this system as the heat and charge are flowing to see what's really going on. Yes?
Okay, not to take away anything from this, but you are comparing theoretical efficiencies of ZTs or Ss against those so-called best materials which are experimental methods. So if you did a comparable calculation, arbitrarily speaking, for bismuth selenide or something like that, one of the materials that you had, if you did a calculation, because you had a number 220 and this is 500, what would that come to? The one showing 220 microvolts.
Well, I don't
You
really,
must have
I
done
don't
the
really
calculation.
have, this would be more like a, excuse me, a band structure calculation for these
Right.
types of materials where it's not really my area of expertise. I don't, it's complicated calculating ZT because you have to have a handle on thermoelectric effects, which are complicated, electrical transport, which is not so bad, and thermal transport, which is also complicated. So it's not so easy to calculate it.
No, what
But-
I'm saying, people must have done the estimates.
The calculations.
Yeah.
I don't know what the degree of agreement is now in the field. I would be surprised if it's like extremely accurate. But so this talk though is not really a talk about thermoelectrics. It's just saying I'm trying to motivate. So Maxwell's demon is supposed to be something that allows you to get more than what you can. Right? We see that in these quantum thermoelectric systems, well, we can't beat the second law, but we do get a lot more, at least theoretically, than what you might expect. Now let's look, but the main focus of this talk is to investigate the fundamental question of what is going on at the microscale in these systems. A separate issue is whether they are, really good for applications, but that's a talk for another day. Okay, so here, I don't know if this is still true, this statement, because I refereed a paper where they achieved 90 microvolts per Kelvin, but I don't know if it's in print yet. So anyway, at the time that I made this slide, this was the highest thermal power across a single molecule, and it was 33 microvolts per Kelvin. It's negative, which means an electron-like transport. And notice, so what they've done here is they've made a temperature difference across the two sides of this buckyball of anywhere between 1 Kelvin and 30 Kelvin. And here they've plotted like the distribution of thermoelectric voltage that they observed. And like I said now, in the meantime, a group from Madrid in similar but not identical molecules has seen thermal power up to 90 microvolts per Kelvin. So the molecules are catching up, at least in thermal power, they're catching up to these state-of-the-art semiconductor thermoelectrics. But now look what's happening here. This is like a couple nanometers, or somebody probably knows better than me, across. What? 10 nanometers? Okay.
No, 1. Sorry, 10 angstroms. Yes.
Okay.
1.
You've put a temperature difference of 30 Kelvin across this 1 nanometer object. So that kind of begs the question, what is the temperature distribution in this thing? Right? I mean, you've really put 30 Kelvin across 1 nanometer. Oops. So that's the kind of thought experiment I want to entertain is, can one think about a temperature gradient across a single molecule and measuring temperature as a function of position across a single molecule? Apparently, there must be something like that, right? I mean, the buckyball is not so much huger than a single water molecule. Well, here's the best that there is currently, the state of the art. It's the scanning thermal microscope in the group here of Pramod Reddy at University of Michigan, I believe it is. And so what he's done is he's taken, there is a commercially available technology, scanning thermal microscope, that you can buy that has a spatial resolution of maybe a micron. It operates in ambient conditions. So the main resolution of the main the main limitation of the spatial resolution is because of convection through the gaseous atmosphere between the probe and the sample that you're trying to investigate. So what they do, they go to ultra-high vacuum. They go to ultra-high vacuum, so you don't have to worry about convection, and also you don't have to worry about like a fluid, like a meniscus forming between the sample and the substrate. And what they've made then is it's like a cantilever, like an AFM cantilever, and on the tip of this cantilever they've mounted a nanoscale thermocouple. And with this thermocouple, they can use this as a thermometer to measure temperature as a function of position. And of course, with the scanning probe techniques, you could obviously have a greater precision than 10 nanometers, but basically the limitation is that their coupling of this tip to the cantilever is about 700 thermal conductance quanta. So the only way they can actually see the sample is if they ram the tip into the contact mode with the sample. And so the contact diameter is around 10 nanometers, so that is the spatial resolution of this thermometer. It's nothing fundamental, it's really just because they need to get better control of the thermal coupling to the environment so that they don't have to go into contact mode. So that motivates us to consider a more idealized situation where you can actually do the scanning in the tunneling mode. So let's try to think about this problem theoretically. What is a nanoscale thermometer for electrons? So I would argue it is an open third terminal of a quantum thermoelectric circuit. So if we go back to the buckyball with the temperature gradient across it, then we would have, let's say, the source and drain electrodes across the buckyball that could supply either a temperature difference or a voltage across the buckyball. Then we want to have our scanning probe come down and measure the temperature. So this probe should serve as a thermometer. What is a thermometer? Well, a thermometer is some small system with some readily identifiable temperature-dependent property which can be brought into thermal equilibrium with the sample. What does thermal equilibrium mean? Well, it means that there should be no net exchange. Once the thermometer has equilibrated, there should be no net flow of either heat or charge into this reservoir. That would represent a local equilibrium with the sample. Now, I emphasize this because many people have thought about what is an electron thermometer. Even going back to my PhD advisor, Phil Anderson. He wrote a paper with Eric Enquist back in 1980, which was one of the very early papers in mesoscopic physics. And they didn't consider the fact that the thermometer also should have zero electrical current flowing into it. It should not only have zero heat current, but zero electrical current. Otherwise, it's not in equilibrium with the sample, right? If it's a sink or source of electrical current, but there's no more heat current flowing, well, it's not in equilibrium, so it's not a good measurement. Now, for the purposes of formalism, of having a simpler formalism, let's look at this problem within linear response. So here I have a notation where IP is the current flowing into the probe, superscript 0 is the electrical current, superscript 1 is the heat current. So if you go to any textbook about transport, whether it be a condensed matter physics textbook or a StatMech textbook, you'll see that there's a general linear response formula for the electrical and the heat currents that involve these linear response coefficients L. You might have heard of them. So the electrical and heat currents flowing into any contact in the system can be expressed in linear response in terms of these L coefficients, and there's terms involving the voltages and terms involving the temperature differences. So if we can theoretically calculate all these coefficients for a situation like this, then we can impose these conditions and solve for the temperature of the probe and plot it as a function of the position of the probe. That's what our goal is. So I feel like I need to now digress and say, how do we calculate these linear response coefficients? So here are some slides from Joshua Barr explaining our theoretical method to do non-equilibrium quantum mechanics. So we have some kind of a junction with our source and drain electrodes and maybe a probe electrode. We start off by solving for the electronic structure of our system of interest. Could be a graphene sheet, could be molecule, whatever, quantum dot. Once we have solved the quantum mechanics of that system, we then find the Green's function that describes the propagation or the dynamics of the electrons in that system. Then here's where the non-equilibrium part comes in. We couple that system then to these electrodes, which are out of equilibrium. And that coupling has two forms. There's a so-called tunneling self-energy, which is described by diagrams like this. And there's also a tunneling correction to the Coulomb self-energy, which, for example, is described by diagrams like this. But anyway, once we have the Green's function, then we can calculate the flow of charge and heat through the junction, and then we can calculate everything we want, such as the temperature seen by such a probe. So the Hamiltonian we take for the reservoirs, the contacts, and the probe, we assume that we just have Fermi gases, and that they're coupled through some kind of quantum system, like so. And we typically, in all the things I'm going to present to you today, the quantum system is a pi-electron system. So we describe that with, in the case of graphene, a tight binding model because it's too big to treat the many-body interactions in the way that we like to do it, or in the case of smaller molecules like benzene shown here, we actually map it onto something like a Hubbard model. Okay, so once we have our Green's functions, we can calculate the flow of charge and heat through the system using this formula, where the superscript 1 is something that we derived a few years back when Justin was a PhD student here. I think I've already told you about this formula in a previous talk, so I'll just say, once we've got these Green's functions, we can calculate the charge and heat currents. These charge and heat currents can be broken down into elastic terms and inelastic terms. The elastic term, this would be the charge or heat current flowing into contact alpha, has an elastic contribution which is essentially given by a multi-terminal generalization of the Landauer-Büdiker formula, where here T alpha beta is the transmission probability of an electron of energy E to go from contact beta to contact alpha, and it's expressed in terms of the Green's functions and the coupling matrices. We call these tunneling width matrices between contact alpha and the system, and between contact beta and the system. So this is, for anybody in mesoscopic or nanophysics, this is a very familiar looking formula. Here nu equals 1 gives the heat current, nu equals 0 gives the electric current in units of the charge of the electron. And we can also calculate the inelastic contribution, which has a form like this. The important thing to notice is in linear response and room temperature, this is really the dominant term in the kinds of systems we're studying. So this term here, we really don't have to worry too much about. It's all coming from this term here. All right, so now we're getting close to the heart of the matter. As I said, we're going to consider linear response just so the formalism is a little more tractable. There's nothing about nonlinear response that poses undue difficulties for us, but it's already very rich, the results in linear response, so let's do that. So in linear response, like I was telling you, all of the response coefficients, such as the electrical conductance, the thermal power, the thermal conductance of two-terminal devices can be expressed in terms of these linear response coefficients. Remember, I had those for the general case. And these, for such a quantum coherent conductor, are simply expressed in terms of the transmission probabilities as follows. Okay, so once we have the Green's function, we can calculate the transmission probabilities. Once we have them, we can calculate these linear response coefficients. Okay, but this formalism is only for two-terminal devices. If we want to have this scanning probe, it's a third terminal, we need a three-terminal formula. So the three-terminal formula is a little bit more complicated. If it's what we call a pure thermal circuit, so if you have a heat transport setup, but where there's no net electrical current flowing, then you can eliminate the electrical currents from the linear response formulas, and you can derive a pure heat transport formula like this. Okay, so this says the heat current flowing into electrode alpha is equal to a sum over all the other electrodes, these thermal conductances between beta and alpha, and the temperature difference between beta and alpha. Okay? And these thermal conductances are somewhat complicated, but they can be expressed in terms of these linear response coefficients in the following way. So the precise form of this formula is probably not that interesting to you. It's familiar from mesoscopic physics that when you have more than two terminals, the algebra starts to get complicated, but it's very easy to do it. Okay, so now once we have a formula like this, we can simply set the heat current into our probe to 0, and we can then solve for the probe temperature. So that's what we do, but we consider yet another terminal, because it would be a drastic idealization not to consider that in addition to the source and drain and the probe, there's also an ambient environment. You don't have to worry about the ambient environment in electrical transport to the same degree because typically the ambient environment is not a source or sink of charge, but the ambient environment is a source and or sink of heat. So it's essential to include the environment when you're modeling a temperature probe. And so it ends up that you can show the temperature of the probe once it's reached equilibrium is given by this simple formula. The thermal conductance between, let's say, the source and the probe times the temperature of the source, plus the thermal conductance between the drain and the probe times the temperature of the drain, plus the thermal conductance between the probe and the environment times the temperature of the environment, and then divided by the sum of those three thermal conductances. So it's a very simple formula. And I've told you how we calculate these. As far as this one, it really depends on the nature of the environment and how it couples to the probe. So, as I said, if you buy a commercial STHM, the dominant contribution to this is just convection through the gas between the tip and the sample. If you go to ultra-high vacuum, in principle, you might be limited by just like a radiative blackbody coupling between the probe and the blackbody radiation around it. However, the best STHM that I showed you is not in that regime. Instead, it's dominated by thermal conductance through the cantilever on which that thermocouple is mounted. Okay, so it has, in their case, they have this kappa P naught is about 700 thermal conductance quantum. Okay, so here we get to the actual results. So I'll start with the simplest system first, which is easiest to understand, I think. And that's a linear conjugated polymer. Okay? So it's basically 1, 2, 3, 4, 5, 6 carbon atoms with the associated hydrogens and with some linker group sulfurs to connect to some gold electrodes, this one being a cold electrode at 275 Kelvin, and this one being a hot electrode at 325 Kelvin. Here I've assumed a symmetric thermal bias, so the environmental temperature is 300 Kelvin. And what you see is, there is kind of like a hot end of the molecule and a cold end of the molecule, but the temperature drop is not monotonic. You get this oscillation, hot, cold, cold. Now this particular one is taken with a thermal coupling between the probe and the environment of about 10 to the minus 4 conductance quanta, which corresponds roughly to the case where the only coupling to the environment of the probe is through blackbody radiation. Okay? On the other hand, if you go to a much larger environmental coupling, in this case 10 conductance quanta, you still see the same qualitative pattern of hot, cold, but notice the difference in scale. Here, the range is over 50 Kelvin, the full temperature bias applied. Here, you only see plus or minus 2 millikelvin. So that's because the sensitivity of this measurement is much poorer because the coupling to the environment is stronger than the coupling to the system, and that's actually the regime in which the best STHMs are still operating if you try to do these kind of nanostructures. So these kind of temperature oscillations in a one-dimensional system, to my knowledge, were first predicted in a paper by Dubey and DiVentra, where they considered like a one-dimensional tight binding chain. So here we're seeing it in this particular system. And I'd also like to point out, although perhaps in this audience this is not so familiar, this is what I needed my dad's help to understand. You can actually understand this temperature pattern by using diagrams of the electronic structure from organic chemistry, which in principle have been understood for well over a century before the advent of quantum mechanics. If you just figure out, let's say, the most relevant electronic degrees of freedom in this molecule and the transport through it are these pi electrons, which contribute basically to the double bonds that form here along this backbone. And if you consider the transfer of an electron from a metal atom over here, representing the electrode, onto this conjugated system, what you see is the only ways that you can do it that don't decrease the number of double bonds are to put this electron here, here, or here. You could put it there, but at the expense of breaking an additional double bond. So energetically, it would be prohibitive. And so you see, if this is the hot electrode, it can put its electrons here, here, or here, i.e. there, or there, or there. And so one thing which doesn't quite come out of this picture is that the proximal orbitals, so this orbital is proximal to the cold electrode, it ends up that the proximity effect is also relevant. So basically the hot electrode can put its electron there, but so can the cold electrode, so you basically get an intermediate temperature. But all the rest of the temperature oscillation you can understand from these kind of diagrams. And I would say it's important, I guess, an important aspect of these diagrams, for my understanding of this problem, is to understand that these are a part of what's holding these molecules together, right? If you would sever these double bonds, the molecule would be dissociated, okay? Because when you start talking about quantum temperature oscillations, there's a bunch of papers trying to explain them away by saying, oh, well, decoherence is going to damp out this effect. You'll never be able to see it. But we know that these molecules are stable at room temperature. We know that these double bonds are there. They're not severed by decoherence at room temperature. So the only way that you could provide, or let's say, to damp out these thermal oscillations, you'd have to supply so much inelastic scattering that you would basically destroy all of these double bonds. But that would require thousands and thousands of Kelvin. It certainly would not happen at room temperature. So we know that that argument doesn't hold any water, because of this connection between the quantum coherence and the actual stability of the structure. So these thermal oscillations, they're really there. They're not going to go away due to decoherence, dephasing, and elastic scattering. The only question is, how can you see them, because they occur on such a short length scale. So that was the first system I wanted to show you, because it's, I think, the simplest to understand. Here's actually the first one that we looked at, which was a benzene molecule. And we considered 3 different junction geometries. This is the so-called para-junction, which is a symmetric contact across the molecule. The ortho junction, which is a contact like that. And the meta-junction, which is a contact like this. And again, what you see are these temperature oscillations. Maybe in the para-junction it's not so clear, because you still have like a hot side and a cold side. But in the ortho junction, it's very clear that it's a non-monotonic temperature dependence. And similarly for the meta-junction. Now the ortho and the para you can explain in exactly the same way as for the linear conjugated molecule. The meta one is a little more complicated. Notice here there's a hot orbital and a cold orbital, but here it's a hot bond and a cold bond, because the actual atom here is essentially of indeterminate temperature, and it's the bonds here which have well-defined temperatures. And that's because of the destructive quantum interference, at this point, basically neither the hot nor the cold electrons can get to this point, and so it's the off-diagonal contributions to the transport that dominate. And so this is, again, this would be a regime where the coupling of the probe to the environment is dominated by just black-body radiation, and here would be when you have a much more substantial thermal coupling to the environment, and you see qualitatively the same features are there, just the scale, the size of the oscillations is reduced. So in order to understand these temperature oscillations in more detail, it's useful, I think, to look at a map of the thermal conductance. So concentrate on this left figure, which is the thermal conductance. This here is just a correction, which I don't really want to get into in this talk. So this is the thermal conductance between the hot electrode, which is over here, and the probe when it is above the sample, right? So when the probe is above this orbital, which is proximal to the hot electrode, there's a large thermal conductance. When it's over this orbital, which are in an ortho configuration relative to the hot electrode, there's also a large thermal conductance. And when the temperature probe is over this orbital, which is in a para configuration relative to the hot electrode, there's also a large thermal conductance. However, if the probe is over this orbital, the thermal conductance is essentially 0. So electron waves simply cannot get from here to there or from here to there. That's the same reason why that is the basis for this quantum transistor that we have the patent for. It's the same basic reason. But as I said, organic chemists have actually understood this before the existence of the Schrödinger equation. So these are the calculated contributing structures that describe charge transfer from a metal atom onto a benzene ring. And again, one way to think of it is just you draw all the diagrams where you've transferred an electron from here to here, but where you've conserved the number of double bonds, and there are only these ways to do it. You can either put the unpaired electron there, or by symmetry there, or you can put it there. There's nowhere else to put it. There's no way that you can put this electron here without breaking an additional double bond. So these terms can occur, but they're energetically suppressed. So the dominant terms are these guys here. So when we go back and look at this temperature, oops, I'm coming the wrong way. This kind of temperature distribution. So we say, for instance, in this one here, if the temperature probe is above, let's say, this orbital here, which is actually closer to the hot electrode than it is to the cold electrode, according to these rules that describe the electronic structure, an electron from the hot electrode simply cannot get there, even though it's closer to the hot electrode than it is to the cold electrode. So the thermometer measures a cold temperature because it's not just selecting electrons at random out of the molecule, but it is actually only taking the ones from the cold electrode. So that we immediately thought of this as kind of an analogy of the Maxwell demon. Because, so here's the analogy. Think of the junction plus the molecule as one container of electrons. The molecule, focus on the molecule. It's getting both hot and cold electrons, but if it was just a box full of electrons, it would have a mixture of hot and cold, so it would have some mean temperature, right? Then the temperature probe comes in, and that's like the second container of electrons. Remember, the temperature probe is like a tunnel coupling to another reservoir. That other reservoir would be the second container of electrons. So now instead of gas atoms, we think of electrons, and the two different containers are the molecule and the temperature probe. Okay, so when the temperature probe, for instance, is above this orbital, then the laws of quantum mechanics, or the rules of covalence according to the chemists of the 19th century, will only allow electrons from this reservoir to come into the probe. But you know that these electrons, they're delocalized in the molecule. The electrons in the molecule can go anywhere they want. So really, you should think that it's just like a container, like a box. It's like just a box for electrons. And you might think, well, the temperature probe should be able to take any of the electrons. But instead, the laws of quantum mechanics say that only electrons from the hot electrode can tunnel into the probe when it's above this orbital. And only electrons from the cold electrode can tunnel into the probe when it's above this orbital. So if you think about it, if you think about the process by which this probe is equilibrating with the sample, when the probe is above this orbital, it's getting cooled off by the molecule until it reaches this temperature of the cold electrode. So there's now being a transfer of heat from the cold electrode onto the molecule whose mean temperature is higher than that of the electrode. So it seems as if it's a violation of the second law. What's going on here? Like I said, these rules of covalence, or just the wave effects in quantum mechanics, really are mimicking the effect of this temperature demon. But yet I can tell you, I can assure you, anybody who's taken 560A with me, that the non-equilibrium Green's function formalism explicitly obeys the second law of thermodynamics. There's no way that you can take that formalism, which is built upon the second law as part of its founding, principles, and then derive an effect which violates the second law. It's impossible. There is no violation of the second law here. Why not? Because the electrons in the molecule remember where they came from. Okay? The reason that you can sort out the hot and cold electrons from the molecule, or why the thermometer can do it, is because as long as they haven't lost their phase coherence, they still remember where they came from. And in particular, the ones from the hot electrode can't even get there. The ones from the cold electrode cannot get here. Okay, so you would have to let them sit in there so long that they lost their phase coherence, and only then would there be a mixing of the electrons, mixing of the hot and cold. Okay, so now I'd like to move on to a slightly different topic, and that is, okay, we've looked at this very extreme quantum regime. How do we cross over back to the regime we're more familiar with, where you just get, let's say, a monotonic variation of temperature from hot to cold? I've tried to explain to you that it's not going to happen because of decoherence or inelastic scattering. There's no way in the world that there's enough decoherence or inelastic scattering to significantly perturb those electron waves on this length scale. Instead, what we found is if you just slightly reduce the spatial resolution of the temperature probe, then they all go away and you can't see them. So here is a slightly bigger molecule, and the temperature distribution here, I always thought it looked like an angry man, so we called that the angry man quantum interference pattern. And so here, okay, I didn't go into enough detail about saying exactly how we modeled this thermometer. We model it as an atomically sharp platinum tip. In this case, it's held with the center of that platinum atom 3.5 angstroms above the plane of the molecule. Okay, and then we've just done a microscopic calculation of the tunneling matrix elements between the tip and the molecule to calculate those transmission probabilities. So what we've done in this calculation, this is just the raw calculation with such an atomically sharp tip. And then what we've done here is by hand, we've convolved the transmission function of the tip with a Gaussian with a half angstrom standard deviation. So you see, oh, it starts to wash out the interference pattern. Here we've convolved the transmission function of the tip with a Gaussian with a standard deviation of 1 angstrom, and now the interference pattern is completely gone, and all you can see is a thermal dipole. So our answer would be the way that you recover the classical Fourier law of thermal conduction is not by physical processes that destroy these quantum effects. It's rather because nobody has yet had a thermometer with a sufficient spatial resolution to observe these quantum effects. The quantum effects are really there if you have sufficient resolution to observe them. There is no physical process that's strong enough to get rid of these quantum effects. And as an aside, okay, it was pointed out to us by one of the referees that it's not so convenient to apply a symmetric thermal bias by cooling one electrode and heating the other. Instead, it's more common to just heat one electrode and leave the other one at ambient temperature. So here's the angry man with a heated electrode and the other one kept at ambient temperature. So you can still see these quantum effects even if you don't have a symmetric thermal bias. Okay, but all this may seem very academic because after all, if the current state of the art is 10 nanometers and I'm telling you that we should look for these oscillations on a length scale of what? Here, this is like, well, 1.4 angstroms, right? So the wavelength here is like roughly 2 to 3 angstroms of these oscillations. So that's a couple of orders of magnitude away from what the experiments can do. But there are other systems that you can study, and in particular, I think graphene is probably the best candidate system in which you could observe these thermal quantum effects. And what I've shown here, like I showed you at the very beginning of the talk, is a graphene nanoribbon with the edges here connected to hot, these are basically covalently bonded to hot and cold metal electrodes. And what I've shown is the temperature distributions for 3 different gating situations of this graphene sheet. So here, the Dirac point is 1 eV above, 1 eV above the chemical, the Fermi level of the metal electrodes. Here it's a half an eV above, and here it's a 20th of an eV above. And so what you see, the wavelength of these temperature oscillations gets longer and longer as you approach the Dirac point. So this is something which I'll explain in a moment, but I'd also like to point out, in addition to the fact that the wavelength of the thermal oscillations is variable or controllable by gating or doping. Also, because the graphene is a very good thermal conductor, the coupling between the sample and the probe is going to be larger than it is in those other systems that I showed, so that's also favorable. So how can we understand this tunable wavelength? Well, here what I've shown in black is the probe temperature across the middle, I think it's the middle of that figure. And in blue is the density of states. And so you see, oh, it looks like actually the temperature oscillations are more or less the same wavelength as those of the density of states. The density of states oscillations are closely related to the Friedel oscillations, which were studied in graphene sheets by Brian Leroy's group. And so they showed that the wavelength of the Friedel oscillations in graphene goes inversely as the energy difference of the electron that's carrying that's involved to the Dirac point. So basically that implies if we just gate the system, we can vary and we can tune the wavelength of these thermal oscillations. So here I have again these 3 different values of gating, and the blue line here represents this formula, the predicted Friedel oscillation wavelength. This is in a power spectrum, so it's an inverse wavelength, but what you see indeed is that by gating the system, you can shift this peak in the power spectrum, and there are other peaks. For instance, there are still short wavelength oscillations here, which would be given by the rules of covalence, but superimposed on that, there's a very long wavelength oscillation that's described by this effect here. Okay, so I'm almost done. This is the last thing I wanted to talk about. So after I got back from my sabbatical, I sent a copy of this preprint to Philippe, and he got quite interested in it, and he and Jonathan started working on it. And he asked an interesting question, which is, well, how much do you know that this temperature that you're measuring is really a property of the system and isn't just determined by the tip sample coupling? So that's become the basis of a new project that I don't have time to go into all details today, but I do just want to show you one simple result. So here, again, is a graphene nanoribbon with a thermal gradient across it. And now I just want to look at the temperature at these 3 points, a cold point, a hot point, and a point with intermediate temperature. And I'm going to keep the temperature probe fixed in position, but I'm just going to, by hand, vary the strength of the coupling between the probe and the sample, just to see if the temperature depends strongly on this coupling. And it does not. So if you see here, I've changed like the trace of the gamma p, what I call the tunneling width matrix that describes the tunneling of electrons from the evanescent, from the apex atom of that platinum tip into the sample. There's a matrix describing that tunneling, and I've here taken the trace of this matrix, and over like 12 decades, there's basically the temperature is completely independent of the value of that coupling. Only when the coupling gets to be above an electron volt, then the widths, basically then the tip is coupling so strongly to the sample that it's starting to change the electronic structure of the sample, broadening out the resonances and everything, and then you get this effect. So I think you can kind of see that if we would go back. It might be easier this way. You can kind of see that from this formula here, right? If you increase the tip sample coupling, you increase the thermal conductance here between the probe and the hot electrode, and the thermal conductance between the probe and the cold electrode, but you also increase the denominator in exactly the same way. So you can kind of understand why you might get a result which is essentially independent of the strength of that coupling. I just wanted to show. You see, here is how those guys depend on transmission. Here is how transmission depends on the coupling. So if you make this coupling very small, well, it's the same thing that appears in both the numerator and the denominator. So essentially, the measured temperature does not depend very strongly at all on the strength or the nature of the tip sample coupling. Of course, the resolution I don't want to go through the whole thing again. Let's just skip. Of course, the resolution of your image depends a lot on the nature of the tip, right? If it's an atomically sharp tip, you can get resolution like this. If it was a more blunt tip, of course, you wouldn't see something with such high resolution. So the measured temperature does depend on the nature of the tip, but does not depend strongly on the, let's say, the size of the coupling to the tip. It does depend strongly on the resolution of that tip sample coupling. So that's all I wanted to say. To summarize what we've done, we've come up with a realistic model of an electron thermometer with atomic resolution, or at least proposed one. We can predict quantum thermal oscillations in all kinds of conjugated systems, from individual molecules to graphene. And we've argued, importantly, that these quantum thermal oscillations are extremely robust with respect to disorder and defacing. There's basically no getting rid of them. We've also shown that they are still observable in a low sensitivity measurement, which is where the current STHM technology is. And we've explained the crossover to the classical thermal conduction mechanisms as being really understandable only in terms of interpreting temperature measurements. In other words, it's not that thermal conduction really is more like Fourier and that this is some aberration. It's really that if you really think of temperature defined on the quantum scale, it inherently has these quantum interference effects, and it's only when you coarse grain over these quantum effects that you recover the kind of classical description of thermal conduction. Thanks for your attention. Yes?
How do these effects depend on the starting temperature that you choose? So all the calculations we're doing at 300.
Yes.
If you cool it down and it provides the same gradient, is there any significant change?
Let me think. I don't think that there would be. Because, if you think about the electronic properties of the system, they're not very different at room temperature than, millikelvin temperature. So I think, these guys wouldn't change much. What you would probably change quite a lot is the coupling to the environment. I think technically it may be challenging to heat the system and still keep it at a very cold, like mean temperature. But I don't think there would be really much difference. Certainly the calculation of these guys would be very, very similar at very low temperatures. So room temperature, it doesn't make that much difference.
Do you expect changes in boundary conditions that you go from narrow ribbon to nanotubes?
Oh yeah,
usually you get frustration or something like that, right?
Sure, yeah, we would get a very different, I don't think I brought it here, but this is like an armchair nanoribbon. If you look at the zigzag, it's very different because in the zigzag you have these edge states.
These are all armchairs.
These ones are. It's the same ribbon, but just 3 different gating values. Yeah, I'm not sure if I have my latest thing here. I don't think I put it on here. I have.
What I was curious about is whether spin entropy would play a role in the zigzags.
Oh, spin entropy, that's a good question. Okay, so here I have some results with a zigzag. And you see it's really quite different. Now here, well, it's like a cold contact in the center, right? And then there's a hot, here the edges, the zigzag edges are heated. So you get a very different temperature pattern depending on the boundary conditions. But you would kind of expect that, right? Because there's a quantum interference effect which does depend strongly on the boundary conditions.
So electron-phonon interactions are explicitly not considered in this case?
Yes, we've not included them in our calculation. In the formalism that I presented, they can be included straightforwardly. So the formalism, I can show you like at what point the assumption that they're not there comes in. So at this point, this is completely general. If you calculate these guys including every kind of interaction imaginable, then this formula is completely general. So all of the formulas that just involve these guys are completely general. It's only then when we go and actually calculate those guys that we have to say what are the interactions in the system. So when I derive this kind of formula, here, I derive this formula for the temperature measured by the probe. This formula is completely general. Assuming that you can calculate these thermal conductances, including your electron-phonon interactions and everything, then this formula will still be true. But in the actual calculation I presented you, we have not included electron-phonon coupling. I would say that in these systems, electron-phonon coupling is a weak effect. It's like a small perturbation on the electronic system. So I wouldn't expect it to be very important.
Phonon energies are tens of eV.
Well, the way that people like to look at electron-phonon scattering because you can see it in like higher derivatives of the current with respect to voltage, right? But if you just look at the current itself, you're not going to see them. It's a small effect. It's a small perturbation. Like the probability that an electron propagating across that graphene nanoribbon is going to scatter from a phonon is probably less than 1%. So if you leave that out, you've got 99% of the correct answer. So it can be important in certain contexts. I don't think we've argued that it would not be very important in this particular context. But of course, depending on the system, if you get a system that has near an instability of induced by electron-phonon coupling, of course, then the effect could be amplified. But that brings up a good point, that in these systems out of equilibrium, which don't have a very strong coupling between the different degrees of freedom, this is the electron temperature. The phonon temperature would be entirely different in this system. Right, so there's no reason when a system's out of equilibrium, the different degrees of freedom do not have to have the same energy distribution. So the temperature of the phonons in the system would not be the same as what I'm showing here. But because we have this probe in the tunneling regime with a vacuum tunneling gap, we believe that the dominant thermal coupling will be via tunneling of electrons. Of course, if you go into the contact regime, you're going to couple with the phonons as well. And we have considered that also, but I don't have any figures with me to show you. But essentially, the phonons, because their wave properties are not correlated with those of the electrons, so they give a background similar to the environmental coupling. That's what we predict anyway. Any final questions? All right, if not, I guess we have some refreshments.